Okay, so let's take a look at the topic of fuels. So there are 4 components to this topic. You need to be able to describe the advantages of the use of carbon-based fuels as sources of energy compared with using them for feedstocks. And by feedstocks, we're talking about things like generating plastics. You need to be able to write balanced equations for the combustion of fuels, which only produce carbon dioxide and water. You don't need to worry about incomplete combustion reactions. However, you do need to know that for all reactions to do with combustion, there will be no number, or otherwise known as the number 1, in front of the fuel, and this will be the only reaction equation where you will have fractions. You also need to be able to describe the undesirable consequences of incomplete combustion, and you need to be able to do some calculations similar to those that we have done for enthalpy of solution. However, this time we are looking for enthalpy of combustion.
The same process applies for all combustion reactions. It is always a fuel burning with pure oxygen, and it is producing a product, always carbon dioxide and water. So let's take a look at some of these classic examples. So in this example here, you can see that we have a jelly bean being burnt in the presence of oxygen, so combusting. And you can see the amount of energy that's being released. You can see how bright that jelly bean is. So this is probably equivalent to what's going on in your body, because jelly beans have got quite a lot of sugar, and we could say that that was equivalent to glucose.
In this demonstration, we're going to sacrifice a gummy bear. Well, to do that, we need to create an oxygen-rich environment. So what we're going to do is we're going to take this salt, potassium chlorate, and we're going to heat it up. And when we heat up the potassium chlorate, it's going to decompose. You recognize that this is a decomposition reaction. The potassium chlorate breaks down into potassium chloride and oxygen. Once we get all that oxygen gas in that test tube, we have an oxygen-rich environment. Oxygen is an oxidizer. It supports combustion. So when we put our gummy bear into there, our gummy bear being made of sucrose, is going to combine with the oxygen gas and it's going to combust. You recognize that this is a combustion reaction because we're combining oxygen with our gummy bear, and we're getting products that include carbon dioxide and water, and also this, a lot of energy in the form of heat and light, which you will see. In fact, we get 5,645 kilojoules per mole of energy that is released.
You can record anytime.
Okay.
As I'm heating this up, the potassium chlorate is going to decompose. So those bubbles that are forming in there, what would the bubbles be?
Oxygen.
That's oxygen, right? So inside our test tube, we are creating an oxygen-rich environment. And oxygen is a very strong oxidizer. It supports combustion. So by making this very oxygen-rich environment in there, when I drop the gummy bear in, it should spontaneously combust.
In this other example, you can see here, we have diamond. Now, diamond is pure carbon, and the only thing that can break down carbon is oxygen. So we can actually combust carbon or diamond in the presence of oxygen. So you can see in this apparatus here, we have carbon or diamond burning in the presence of pure oxygen to form carbon dioxide.
I don't suppose, by the way, I mean, you very kindly lent us your gold, but I don't suppose you have a spare diamond on you, do you?
Well, I don't myself, but my wife actually has one.
Oh.
Hope I get it back.
Thank you, Mrs. Croto. Of course, yes. It's the diamond comes out quite easily, doesn't it? Yes. But we can see it more clearly now, though, so can't we? Look at that. This is beautiful. What a beautiful diamond. So it is a real diamond, though, is it?
It's as real as you can get.
Oh, it's quite stunning. So, but course, we want to show that this graphite is made up of carbon. And there's one way we can do this. We can burn our carbon in oxygen, and we'll get, what will we get?
Carbon dioxide.
Carbon dioxide, see, it's pretty good. Yep, carbon dioxide, yes. And then if we bubble that through lime water...
Oh, calcium carbonate.
Calcium carbonate. That's the test for carbon dioxide, of course. And it'll be white. Oh, I didn't ask you that one. Yeah,
No.
just getting carried away now. Right.
Okay.
Anyway, let's just see this over here. So we have some apparatus, and this is where we're going to burn some graphite, all right, and show that it is made of carbon. So what's bubbling through here is just oxygen. This won't react with our lime water at all. Okay, and we're going to see if we can light the graphite and get it burning inside the oxygen. And, there we are. Thank you. That's great. So now we have a hydrogen flame. So this won't produce anything. It's only going to produce water. You can see the water just beginning to condense. Beautiful. I'm going to turn the flame off. Look at that. What do you think?
It's brilliant.
I think it is literally brilliant, yes. This is the carbon combining with the oxygen that's flowing through here. And hopefully we're going to see this changing colour, giving us the milky colour. Yeah, showing that there's carbon dioxide present. I mean, I think we should test diamond as well, don't you? What do you think? Yes? Does Mrs. Croto mind?
Okay.
Okay, in the name of science. Well, that's very kind of you. Harry seems a little nervous. You sure it is a real diamond?
Well, I think it's real diamond, yes, I'm sure.
Well, actually, let's give it a go then. So we'll just put it on there, and again, we'll put this on here. Right. So we have our flame. Here we go. The moment of truth. Now, can we get our diamond to burn in the oxygen? I think that. Oh, look at that.
I hope you can afford to pay for that.
Well, the good news is, Harry, it is a real diamond. Okay? I think this is absolutely stunning. I mean, that diamond there is, it is burning in oxygen. It's combining with the oxygen of the air. Have you ever seen a diamond burning like that before?
No, I haven't.
No, it is quite stunning to see, isn't it? And remember, there are no flames coming from this. So this is just, again, the heat of the reaction as the carbon combines with the oxygen that's present flowing through here, forming carbon dioxide. Oh, that is absolutely stunning. Just look at that. It's glowing all by itself. It's absolutely brilliant. I think that's amazing. And look, our lime water is going milky.
It's the most expensive lime water I've ever seen.
Actually, I think you're probably right there. It really is the most expensive lime water that you've ever seen.
Here you're going to see a series of experiments that demonstrate different fuel sources, but they all show combustion. You'll also be able to see the carbon dioxide being produced and the evidence for that.
But what exactly happens when things burn? Obviously, a lot of energy is given out, and heat and light and so on. But where do things go? So these candles here, when they're burning in the air, well, what happens? We see the light and heat is given out, but eventually they disappear. There's nothing left. Well, the candles are made of solids called hydrocarbons. Hydrocarbons are substances that contain carbon and hydrogen only, and petrol is an example of a hydrocarbon. It's a liquid hydrocarbon. We also see gas hydrocarbons as well, and we'll see some of these later, but this is a solid. But nonetheless, when these burn, they combine with the oxygen, and what we end up with is carbon dioxide gas and water. Now, we can show this using the apparatus here. What we're going to do in a minute is draw the gases that are being given out as the candles burn through the funnel, and we have a test tube here that's been cooled. So this is being cooled down so we can condense any water vapor that might be given out. And the solution in this flask here is called lime water. And this reacts with carbon dioxide gas, and in the presence of carbon dioxide, a white, milky-coloured precipitate forms. So we need to keep an eye on this when I put the candles on there to see if we can see it changing from the clear colourless solution there to a sort of milky white solid forming. So put the candles in here, the gases are being drawn through the apparatus, and already you can see the lime water beginning to change. It's beginning to go milky now. This is the formation of, well, it's essentially chalk. giving us a white precipitate in this. So this is the carbon dioxide that's being given out as the hydrocarbons are burning. So the carbon in them is forming carbon dioxide. And if we look in the test tube, we might be able to see a few drops of water beginning to form. In fact, we can see there's a few drops in here and in the tube at the top, and a little drop about to drip down, I think, into the bottom there. So water vapour is also being produced during this combustion.
So you need to know the combustion reactions. The other key things with combustion reactions is that there always needs to be a number 1 in front of the fuel. Now, because as chemists we know if there's nothing there, then we assume it's a number 1. So there will be no number in front of the fuel, and you'll balance the rest of the equation. This is the only reaction equation where you may have a half value.
Let's take a look at the advantages and disadvantages of using carbon-based fuels as sources of heat energy compared with using them for feedstock. And when we say feedstock, we're talking about polymers, so we're comparing using them for burning in our cars or for energy in that way compared with making polymers out of them. Alright, so the key advantages in using fossil fuels for combustion is that they're really easily extracted. We've got the process down to a fine art, we know what we're doing, we can distill off the things that we need and utilise what we need. It's also really easy to remove any impurities, and because it's a liquid, they're fairly easily transported. And if we compare this with things like the hydrogen fuel cell, we're looking at transporting gases which are a lot more dangerous to transport. There are some disadvantages though. We are running out of fossil fuels. We have a limited supply and they're a non-renewable source. So once we've run out, that's it. They're also in places that are really hard to extract. So we often find them in deep seas, and we see the oil wells out in the middle of the ocean, which makes them dangerous. It also makes the risk of spillage a lot greater. There's also a risk of accidental combustion. So because the fuels that we use are very flammable, and you'll have seen this around the petrol stations, when you go to the petrol station, beware of matches, beware of using your phone. We don't need any ignition switch because they are very, very combustible and therefore explosive. And as you would also know, it reduces the air quality. So the quality of the air when fuels are being combusted produces things like carbon dioxide, potentially carbon monoxide from incomplete combustion, soot, nitrogen oxides. All of these things reduce the quality of the air. These are shown in a little bit more detail in your Essentials book from pages 140 to 142, and it goes through it really clearly there as well. Okay, so what about using them to create polymers? So we can turn oils into synthetic polymers. So they're things like plastics, and you're probably using synthetic polymers in everyday life. The advantages is that they can be fairly readily turned into these synthetic polymers, which includes things like medicine, organic solvents, oil-based paints, synthetic materials. And when these products are finished with, they can be either recycled or burnt to get the energy back out of them. There are some disadvantages, however. They can be very difficult to recycle, and in that recycling process they can release toxic gases while they're being burnt. They also have both complete and incomplete combustion. So if a fuel's not completely burnt, we are going to get incomplete combustion products, being things of carbon monoxide and carbon as well. More details on this can be found on pages 142 to 143 and in 310 as well. Alright, so let's look at the undesirable consequences of incomplete combustion. The two key features that we're worried about in this section are soot and carbon monoxide, but you would also know of some others from in topic 1. When we talked about unburnt hydrocarbons, we also talked about the nitric oxides. So let's take a look at soot. You often see it like this charcoal powder, and this is what you'll see when cars aren't functioning well, and you'll often see that black powder coming out of the back of cars or trucks. So that black powder is carbon, and it's pure carbon. And we often see it, because we see it as a fine powder, we see it as a smoke. So if something, if soot lands on surfaces, it can blacken them and damage them, but it also causes that visual pollution, so it can cause that darkening of the air. In doing that, it can also clog up air and fuel inlets, which makes their burning less efficient. If it falls onto the leaves of plants, it can reduce the ability for plants to go through the photosynthesis process, which therefore reduces the amount of oxygen in the air. It can also kill the plants if there's enough of it on there. And finally, it can have harmful respiratory problems such as bronchitis, asthma, and emphysema. And what about carbon monoxide then? Carbon monoxide is very toxic. So it's generally caused from the incomplete combustion, obviously, but generally we see it in urban areas. If carbon monoxide is left in the presence of oxygen for long enough, it will turn into carbon dioxide. If it doesn't, however, we can get carbon monoxide interfering with the hemoglobin in the body. So hemoglobin is a really important element in the body, and it binds to the oxygen and transports the oxygen around the body. If we have carbon monoxide, it displaces the oxygen. So instead of, we can see here the oxygen's binded to the hemoglobin. In the presence of carbon monoxide, it will bind to the hemoglobin and release the oxygen. This means that the oxygen is not free to be transported around the body. And we can see this is an equilibrium reaction because it has the same number of molecules on both sides, which we'll have a look at again in equilibrium reactions. But because of this same number of molecules, it is a very balanced equilibrium. And so this is actually a very serious problem for anyone who has carbon monoxide poisoning. And to deal with this, they need to go into specialized pressure chambers.
Combustion, when we combust something, we get energy produced. And to measure the amount of energy produced, we will tend to use the combusting product to heat a known amount of water a certain temperature. So we would continue to combust things until such time as we got a known rise in temperature. So if you take a look at this apparatus, which you'll be using in the lab, you can see underneath we have a oil burner, and in this case it's an alcohol burner, burning a particular alcohol. So you would light the wick, and then you'll be using that to heat up the water at a known temperature. Then you'll be able to measure the number of moles that you have used of that particular alcohol. Now there are some limitations with this as a method. So you can see that the canister used for heating is metal. That means that heat is gained fairly rapidly through the oil burner or the alcohol burner. And that's important because otherwise we're not going to get that transferred to the water. But it also means that heat can be lost fairly rapidly to the surroundings. To minimize the impact of these errors, instead of heating at 1 degree, we're heating at 10. But that also means that it has to be heated for a larger amount of time, which means more heat can be lost to the surroundings. In addition, you could repeat this experiment several times, which would minimize the impact of random errors on the results. Okay, so let's address the idea of combustion. Combustion is when we have fuels reacting with oxygen and only oxygen to form carbon dioxide and water as the byproducts. So when we have this complete combustion occurring, it assumes that all of the fuel has reacted with only oxygen. This doesn't always happen, and you've probably seen this around. When we get incomplete combustion, we often get carbon, otherwise known as soot, and that's that black charcoaly coloured product. So part of the problem with that could be the purity of the air that we've got. It could also be the ratio we've got the fuel in. And this links back to what you already learnt in topic 1. So we also have the other products in the air. which could give us things like nitrogen dioxide or nitrogen oxide. Right. So another couple of examples of a combustion. So combustion is also the process of respiration. So when we're talking about combustion in our bodies, we're talking about the respiration process in which our bodies convert the fuel, otherwise known as glucose, into carbon dioxide and water. And then we breathe that burnt fuel out as carbon dioxide. So the other thing that you need to be able to do is do some calculations given the right amount of information. So let's take a look at a sample calculation of a combustion reaction.
Okay, so let's take a look at a worked example. Firstly, let's write the equation for the complete combustion of glucose. So the equation for any time that we are doing combustion is fuel plus oxygen goes to form carbon dioxide and water. And if we go through and then start to make the state for the fuel will depend on what we are using. The state for the oxygen is always gas, carbon dioxide is always gas, and the water is a liquid. Now, important to note with this, these combustion reactions are worth 4 marks. So the first mark is for writing the equation correctly. The second mark is for balancing the equation correctly. The third mark is for putting the states in. The one thing I haven't now put in is the enthalpy of combustion. So I'd actually need to add for the 4th mark, the delta H value. You're not given this yet because that's something that you need to calculate. So once you've calculated that, you'd need to have that in the equation here to get your 4th mark. So what about the equation in this reaction? So we have glucose undergoing complete combustion. So let's start writing glucose. We're given it in the equation. So we have C6H12O6. Now it's important to note here that we are talking about solid glucose. So the state symbol for that's going to be solid. Now it's a combustion reaction, so it's burning in the presence of oxygen, and that's a gas, and it's going to form carbon dioxide and water. So we'll add our symbols in there again. So next thing that we need to note is what we do now to balance this. So let's go through and balance the carbons first. So we've got 6 carbons, which means we need a 6 in front of carbon dioxide. That now gives us the carbons. Let's have a look at the hydrogens. We need 12 of them, so we'll go ahead and put a 6 in front of the water. We now have 12 oxygens here and 6 here, giving us a total of 18. So let's see how many we've got. So we have 6 oxygens here, and we're going to need another 12. So to do that, we'll just put a 6 in front of the oxygen, and now we have a balanced equation. There's our 3 of our 4 marks. We need to have the delta H symbol here to get our 4th mark, but to do that, we actually need to calculate it. So let's go through and do that now. All right, so you should remember before that we had our delta H equation. So delta H equals the change in temperature times by the mass times by the heat capacity of water, which is always 4.18. And we then divide that by the number of moles times by 1000. So because of the way this reaction was set up, the temperature of the water was changed. So if we have a look at the change in temperature here, so we've gone from 21.5 degrees to 26.1, which is a change of 4.6 degrees. We're interested in the mass, but we're only interested in the mass of the water, and so we can see that we've used 1000 milliliters, which is the same as 1 litre, times by heat capacity, which I said before was 4.18. We're going to divide that by number of moles times by 1000. So we can do the times by 1000 bit now. Okay, so let's calculate the number of moles. Remember that number of moles equals mass on molar mass. and the mass of the glucose happens to be 1.22 grams. So reading that straight from the question. To calculate the molar mass of glucose, we're going to add up the carbons, the hydrogens, and the oxygens. And that's so by doing that, we end up with 180.1559, and then we do our calculation of division to get the number of moles. And that gives us 0.00677 moles. And so if we put that back into our formula, 0.006677, and we complete our calculation here, so timesing out our top line and dividing it by our bottom line, we end up with delta H equal to 2.88 kilojoules per mole. It's the -1. And so that then becomes our delta H, and we can put that back into our combustion reaction. And knowing that this is giving off heat, it means that we've got a minus delta H, so it's minus 2.88 kilojoules per mole. So take a look at this reaction in action, and you'll see the combustion of a jelly baby showing the energy given off.